We'll take up two problems which were left out earlier in the topic of continuity and differentiability, specifically to continuity. Question number 12. F of x is equal to modulus of x upon x. X is not equal to 0. So x is greater than 0 and x is less than 0. Okay. And f of x equal to 0 when x is equal to 0. Fine. They are not very clear where to discuss the continuity. One thing for sure we know we have to discuss the continuity at 0. That is for sure. So we have to discuss the continuity at x equal to 0. Then we have to discuss the continuity for all values of x which is less than 0, for all values of x which is greater than 0. Okay. And in this problem, I'll also explain you the concept of removable or non-removable discontinuity. So first we'll start with x equal to 0. At x equal to 0, LHL is equal to limit x approaching 0 minus 0 minus is x less than 0. Okay. So x less than 0 is this function modulus of x upon x. Okay. So change the limits 0 minus h. Limit h approaching 0 minus h modulus upon minus h upon minus h which is minus 1. So at x equal to 0 we'll find out the RHL as well. X approaching 0 plus x greater than 0 RHL modulus of x upon x 0 plus h 0 plus h. Okay. So modulus of h upon h which is 1. So LHL is not equal to RHL because LHL is minus 1, RHL is 1. Okay. Now I'll tell you a few things. F of x equal to 0 when x is equal to 0. Now LHL is minus 1, RHL is 1, f of x equal to 0 is 0. So certainly all three things are not equal. Therefore it is discontinuous at x is equal to 0. Correct? In this case, we cannot remove the discontinuity. Generally, we remove the discontinuity by redefining this particular value. But then this value cannot be changed in this problem because LHL and RHL are different. Okay, so if both are different, so we cannot remove the discontinuity. Now, if suppose LHL and RHL both are minus 1, then we can remove the discontinuity. We can eliminate this 0 and we can write minus 1 over here. So in this case, we have to write that the discontinuity can be removable and this is the function. Okay, but then as per our problem that we have solved, we have to mention that if they're asking, then we have to mention discontinuity cannot be removable because LHL is not equal to RHL. Okay. Now x is less than 0. Okay. 0 we did. Now x is less than 0. So for less than 0, the function is same. Less than 0, the function is same. Modulus of x upon x. So for any value of x which is less than 0, these are all negative values. So all x values will be negative. There won't be a single positive value. So this is x upon minus x which is minus 1. So for any real value of x which is less than 0, we get a constant function and constant function is always continuous. So for any real value of x which is less than 0, we get a constant function. Therefore, it is continuous at any real value of x which is less than 0. Okay. Now x greater than 0, this values. So f of x is equal to modulus of x upon x. So for any x which is greater than 0, all x values will be positive. All x values will be positive. So it will be 1. So you take any value of x, the answer is going to be 1, which is a constant function. Therefore, it is continuous at any real value of x which is greater than 0. Final conclusion in this problem, it is discontinuous at x is equal to 0. It is continuous at any real value of x which is greater than 0 or which is lesser than 0. Fine. Yeah. Let's go to question number 12b. F of x is equal to x upon modulus of x. X is less than 0 and f of x is equal to minus 1. X is greater than or equal to 0. Here also they have not mentioned where we need to check discontinuity. So we have to check discontinuity at x equal to 0. 0 is the critical point. Then x greater than 0 for all values of x which is greater than 0 and less than 0. So for every real value, we need to check the discontinuity or discontinuity. We'll start with 0. 0 has to be very specific. It is a critical value. So at 0, at x equal to 0, LHL equal to limit x approaching 0 minus 0 minus is x less than 0. So that function is x upon modulus of x. So h approaching 0, 0 minus h upon modulus of 0 minus h. 0 minus h is minus h. Modulus of minus h which is h. Okay. So this is going to be minus 1. Okay. See, modulus of minus h is h, but then upper ka minus h will remain as it is. RHL limit x approaching 0 plus x is greater than 0, x upon modulus of x, limit h approaching 0, 0 plus h, 0 plus h, limit h approaching 0, h upon modulus of h, modulus of h is h. Okay. So 0 plus h is h, modulus of h is h. So this is going to be 1. Okay. Let me just go back and check. Sorry, I just made a small error. For x greater than 0, the function is not this. The function is minus 1. Sorry for that. So this was actually not required. You need to keep on checking the question, otherwise this kind of errors might occur. So limit for 0 plus x greater than 0, the function is minus 1. Limit of a constant is constant. So both are minus 1. So, and the third thing, f of x equal to 0, that is also equal to minus 1. Okay. X equal to 0 is also minus 1. So all three things are equal. So it is continuous at x equal to 0. Now x less than 0. F of x is x upon modulus of x. Now less than 0, x values are negative. Every value of x is negative. So this is minus x upon modulus of minus x is x, which is equal to minus 1. It's a constant function. So when x is equal to minus 1, minus 2, minus 3, minus 0.999, minus 0.5, any value of x which is less than 0, any real value of x which is less than 0, the function is continuous because it's a constant function. That conclusion you need to give. Now for x is greater than 0, f of x is equal to minus 1. It's given in the problem. So you for any value of x which is greater than 0, that is 1, 2, 3, 0.1, 0.5, 0.8, any real value, decimal, non-decimal value which is greater than 0, the function is a constant function. Therefore, it is continuous at every real value of x which is greater than 0. So the final conclusion, at 0 it is continuous, at greater than 0 it is continuous, at less than 0 any value of x is continuous. LHL, RHL was done only for 0 because 0 is the critical value in the problem. Okay. So do these two problems as well.